A Bose-Einstein condensate is a state of matter of a dilute gas of bosons cooled to temperatures very close to absolute zero. Under such conditions, a large fraction of bosons occupy the lowest quantum state, at which point macroscopic quantum phenomena become apparent. It is formed by cooling a gas of extremely low density, about 100,000th the density of normal air, to ultra-low temperatures. This state was first predicted, generally, in 1924-25 by Satyendra and Nath, Bose and Albert Einstein. History. Satyendra and Nath Bose first sent a paper to Einstein on the quantum statistics of light quanta, deriving Planck's quantum radiation law without any reference to classical physics, and Einstein was impressed, translated the paper himself from English to German and submitted it for Bose to the Zeitschrift für Physik, which published it. Einstein then extended Bose's ideas to matter in two other papers. The result of their efforts is the concept of a Bose gas, governed by Bose-Einstein statistics, which describes the statistical distribution of identical particles with integer spin, now called bosons. Bosons, which include the photon as well as atoms such as helium-4, are allowed to share a quantum state. Einstein proposed that cooling bosonic atoms to a very low temperature would cause them to fall into the lowest accessible quantum state, resulting in a new form of matter. In 1938, Fritz London proposed Becker's mechanism for superfluidity in Fourier superconductivity. On June 5, 1995, the first gaseous condensate was produced by Eric Cornell and Carl Wieman at the University of Colorado at Boulder NIST JILA lab, in a gas of rubidium atoms cooled to 170 nanokelvin. Shortly thereafter, Wolfgang Cattoli at MIT demonstrated important Beck properties. For their achievements, Cornell, Wieman, and Cattoli received the 2001 Nobel Prize in Physics. Many isotopes were soon condensed, then molecules, quasi-particles, and photons in 2010. Experimental observation. In 1938, Pyotr Karpatzer, John Allen and Don Misner discovered that helium-4 became a new kind of fluid, now known as a superfluid, at temperatures less than 2.17 K. Superfluid helium has many unusual properties, including zero viscosity and the existence of quantized vortices. It was quickly believed that the superfluidity was due to partial Bose-Einstein condensation of the liquid. In fact, many properties of superfluid helium also appear in gaseous condensates created by Cornell, Wieman, and Cattoli. Superfluid helium-4 is a liquid rather than a gas, which means that the interactions between the atoms are relatively strong. The original theory of Bose-Einstein condensation must be heavily modified in order to describe it. Bose-Einstein condensation remains, however, fundamental to the superfluid properties of helium-4. Note that helium-3, a fermion, also enters a superfluid phase at low temperature, which can be explained by the formation of bosonic Cooper pairs of two atoms. Gaseous. The first pure Bose-Einstein condensate was created by Eric Cornell, Carl Wieman, and co-workers at JILA on 5 June 1995. They cooled a dilute vapor of approximately 2,000 rubidium-87 atoms to below 170 Nk using a combination of laser cooling and magnetic evaporative cooling. About 4 months later, an independent effort led by Wolfgang Cattoli at MIT condensed sodium-23. Kettle's condensate had 100 times more atoms, allowing important results such as the observation of quantum mechanical interference between two different condensates. Cornell, Wieman and Kettle won the 2001 Nobel Prize in Physics for their achievements. A group led by Randall Hullett at Rice University announced a condensate of lithium atoms only 1 month following the JILA work. Lithium has attractive interactions, causing the condensate to be unstable and collapse for all but a few atoms. Hewlett's team subsequently showed the condensate could be stabilized by confinement quantum pressure for up to about 1,000 atoms. Various isotopes have since been condensed. Velocity distribution data graph. In the image accompanying this article, the velocity distribution data indicates the formation of a Bose-Einstein condensate out of a gas of rubidium atoms. The false colors indicate the number of atoms at each velocity, with red being the fewest and white being the most. The areas appearing white and light blue are at the lowest velocities. The peak is not infinitely narrow because of the Heisenberg uncertainty principle. Spatially confined atoms have a minimum width velocity distribution. This width is given by the curvature of the magnetic potential in the given direction. More tightly confined directions have bigger widths in the ballistic velocity distribution. This anisotropy of the peak on the right is a purely quantum mechanical effect and does not exist in the thermal distribution on the left. This graph served as the cover design for the 1999 textbook Thermal Physics by Ralph Biolin. Quasi-particles. Bose-Einstein condensation also applies to quasi-particles in solids. Manyons, excitons, and polaritons have integer spin and form condensates. Manyons, electron spin waves, can be controlled by a magnetic field. Densities from the limit of a dilute gas to a strongly interacting Bose liquid are possible. Magnetic ordering is the analog of superfluidity. In 1999, condensation was demonstrated in antiferromagnetic TLC-UCl3 at temperatures as large as 14 K. The high transition temperature is due to the manyon's small mass and greater achievable density. In 2006, condensation in a ferromagnetic yttrium-ion garnet thin film was seen even at room temperature with optical pumping. Excitons, electron-hole pairs, were predicted to condense at low temperature and high density by Bohr et al. In 1961. Bilayer system experiments first demonstrated condensation in 2003 by Hall voltage disappearance. Fast optical exciton creation was used to form condensates in sub-Kelvin in 2005 on. Polariton condensation was detected in a 5K quantum well microcavity. Current research. Compared to more commonly encountered states of matter, Bose-Einstein condensates are extremely fragile. The slightest interaction with the external environment can be enough to warm them past the condensation threshold, eliminating their interesting properties and forming a normal gas. Nevertheless, they have proven useful in exploring the wide range of questions in fundamental physics, and the years since the initial discoveries by the JILA and MIT groups have seen an increase in experimental and theoretical activity. Examples include experiments that have demonstrated interference between condensates due to wave-particle duality, the study of superfluidity and quantized vortices, the creation of bright matter wave solitons from Bose condensates confined to one dimension, and the slowing of light pulses to very low speeds using electromagnetically induced transparency. Vortices in Bose-Einstein condensates are also currently the subject of analog gravity research, studying the possibility of modeling black holes and the related phenomena in such environments in the laboratory. Experimenters have also realized optical lattices, where the interference pattern from overlapping lasers provides a periodic potential. These have been used to explore the transition between a superfluid and a Mott insulator, and may be useful in studying Bose-Einstein condensation in fewer than 3 dimensions, for example the Tonks-Gerardo gas. Bose-Einstein condensates composed of a wide range of isotopes have been produced. Cooling fermions to extremely low temperatures has created degenerate gases, subject to the Pauli exclusion principle. To exhibit Bose-Einstein condensation, the fermions must pair up to form bosonic compound particles. The first molecular condensates were created in November 2003 by the groups of Rudolf Grimm at the University of Innsbruck, Deborah S. Ginn at the University of Colorado at Boulder, and Wolfgang Kettli at MIT. Ginn quickly went on to create the first fermionic condensate composed of Cooper pairs. In 1999, Danish physicist Leen Howe led a team from Harvard University which slowed a beam of light to about 17 meters per second, using a superfluid. Howe and her associates have since made a group of condensate atoms recoil from a light pulse such that they recorded the light's phase and amplitude, recovered by a second nearby condensate, in what they term slow light-mediated atomic matter wave amplification, using Bose-Einstein condensates. Details are discussed in Nature. Researchers in the new field of atomtronics use the properties of Bose-Einstein condensates when manipulating groups of identical cold atoms using lasers. Further, BECs have been proposed by Emmanuel David Tannenbaum for anti-stealth technology. Isotopes. The effect has mainly been observed on alkaline atoms which have nuclear properties particularly suitable for working with traps. As of 2012, using ultra-low temperatures of 10-7 K or below, Bose-Einstein condensates had been obtained for a multitude of isotopes, mainly of alkaline metal, alkaline earth metal, and lanthanide atoms. Research was finally successful in hydrogen with aid of special methods. In contrast, the superfluid state of 4He below 2.17 K is not a good example, because the interaction between the atoms is too strong. Only 8% of atoms are in the ground state near absolute zero, rather than the 100% of a true condensate. The bosonic behavior of some of these alkaline gases appears odd at first sight, because the nuclei have half-integer total spin. It arises from a subtle interplay of electronic and nuclear spins, at ultra-low temperatures and corresponding excitation energies. The half-integer total spin of the electronic shell and half-integer total spin of the nucleus are coupled by a very weak hyperfine interaction. The total spin of the atom arising from this coupling is an integer lower value. The chemistry of systems at room temperature is determined by the electronic properties, which is essentially fermionic. Since room temperature thermal excitations have typical energies much higher than the hyperfine values,